All right, let's just jump straight into this animated explainer. Today, we're taking a look at a really fascinating concept, how our universe seems to operate on these absolutely perfect, beautiful mathematical laws, right up until the exact moment those laws completely and spectacularly break down.
We all kind of like to think of reality as this perfectly tuned machine, right? But we're going to look at some undeniable mathematical paradoxes that strongly suggest otherwise. So the big question is, does the universe actually follow a master equation? Or at its core, is it fundamentally broken?
So here's our roadmap for today. We'll start with the rules of reality, move into time and thermodynamics, check out quantum spookiness and entanglement, see exactly where the math breaks, and finish up with some unsolved universal mysteries. Let's get into it.
Starting off with Section 1, the rules of reality, the beautiful engine. This is where nature always seems to know exactly what it's doing.
Looking back, some of history's greatest minds realized a pretty shocking truth. Back in 1657, Pierre de Fermat figured out that light bending from air to water is actually just taking the path of least time. Then in 1696, Bernoulli challenged folks to find the fastest path for a falling object, giving us the cycloid curve. Fast forward to the 1750s, and Euler and Lagrange wrapped this all up into the principle of least action. Basically everything, from a refracting ray of light to a falling object, is literally just nature perfectly optimizing its path.
Fermat actually proved that light, in a way, calculates the fastest possible route. And he was so blown away by this that he called it the most extraordinary, the most unforeseen, and the happiest calculation of my life. It showed that classical physics is built on this incredibly elegant optimization principle. Nature just naturally does the most efficient thing.
And this perfectly tees up Noether's theorem. Emmy Noether mathematically proved that the fundamental symmetries of space and time are exactly what guarantee our conservation laws. Because the laws of physics don't change as you move through space, we get the conservation of linear momentum. Because they don't change over time, we get the conservation of energy. And rotation gives us angular momentum. It is just a perfectly balanced equation.
But what actually happens when these perfect laws are forced to agree with each other? Well, that brings us to Section 2, time and thermodynamics. This is where the paradoxes begin.
So let's talk about a supposedly unbreakable rule, the second law of thermodynamics, which says entropy always has to increase. Back in 1867, James Clerk Maxwell set up this massive conceptual trap. He imagined a microscopic demon guarding a door between two gas chambers, right? It only lets the fast, hot molecules pass one way and the slow, cold ones the other. Theoretically, this intelligent little sorter could reverse entropy and create a temperature difference without doing any actual physical work. It's a total mind-bending.
The real kicker here is the deep contradiction between math and reality. See, Newton's and Maxwell's equations are mathematically completely reversible. They work flawlessly, forwards or backwards in time. But in the real world, physical irreversibility rules everything. Broken glass never just reassembles itself, and smoke never flows back into a fire. So while the math of classical physics is entirely blind to the direction of time, reality insists on this one-way arrow of time driven by entropy.
And even when the universe perfectly follows the rules, we crash right into chaos theory. This tells us that deterministic systems can still be wildly unpredictable. Because of this super high sensitivity to tiny microscopic changes in starting conditions, complex systems like our weather, for example, become fundamentally impossible to predict long-term. So the rules apply, sure, but the final outcome is just pure chaos.
Moving right along to Section 3, quantum spookiness and entanglement. We're zooming out of the macro world now to see how reality's engine completely glitches out at the microscopic level.
Down in the quantum realm, particles exist in a superposition of states, meaning they juggle multiple, overlapping possibilities at the exact same time, until they're actually measured. Now, when two qubits become maximally entangled, they enter something called a Bell state. In this specific state, measuring one qubit instantaneously dictates the possible values of the other one, literally no matter how far apart they are. To really grasp how bizarre this is, let's use physicist Brian Greene's analogy. Imagine you have entangled boxes on Earth and Vulcan. If their internal states were just secretly pre-programmed from the start, what physicists call hidden variables, basic probability says they should match at least 55% of the time when you measure them randomly. But quantum entanglement yields exactly a 50% match. John Bell used this to prove mathematically that these particles aren't secretly pre-programmed. Their connection is genuinely spooky and entirely non-local.
Amazingly enough, we actually use this glitch to our advantage in quantum teleportation. It works like this. Alice sends qubits through a CNOT gate, passes the first one through a Hadamard gate, measures them, and then sends just the classical data over to Bob. Bob then does a few operations on his entangled half, and boom, he completely recovers Alice's original quantum state. We're literally transferring exact quantum information across distances without physically moving the original state itself. How wild is that?
But here is the ultimate glitch, the measurement problem. Schrödinger's equation perfectly describes those overlapping possibilities before observation. And sure, we can measure the definite outcome after observation, but the math offers absolutely no mechanism for the transition itself. Physics still cannot explain the exact instant a measurement forces reality to choose a state. Are there hidden variables? Are there infinite parallel universes branching off? Honestly, we just don't know.
Okay, things are about to get even weirder in Section 4, where the math breaks. Let's look at the exact places where our most trusted, battle-tested formulas just spit out literal impossibilities.
Take the center of a black hole, for instance. Einstein's beautifully elegant equations of general relativity predict an infinite density compressed into zero volume. Now, in mathematics, division by zero is totally undefined. In physics, this undefined outcome manifests as a singularity. It's basically the universe's version of a fatal computer crash, a place where physics itself just has no answer.
And consider this absolutely staggering number, 10 to the power of 120. This is the discrepancy between the predicted vacuum energy of empty space calculated by quantum field theory and what we actually observe in reality. To put that into perspective, if you were this wrong about the number of atoms in the entire universe, you'd be laughed out of the room. It's widely regarded as the largest error ever calculated in physics. We've got two perfect theories producing a catastrophic contradiction when we ask them to agree.
Even the equations keeping airplanes in the sky right now carry a bit of a dark secret. The Navier-Stokes equations are the absolute mathematical backbone of fluid dynamics. We use them for everything from designing jets to predicting the weather. Yet, as a pure mathematical proof, nobody can actually guarantee that a perfectly smooth fluid won't suddenly, in finite time, develop a point of infinite energy. It's a phenomenon called blow-up. We just kind of assume it won't happen, but we literally cannot mathematically prove it.
Finally, let's explore Section 5, Unsolved Universal Mysteries. We're going to look at the pure mathematics that underpin all these physical laws.
So, a long time ago, Euler proved a really bizarre fact. An infinite sequence of inverse squares adds up to precisely pi squared over 6. Building on that crazy logic, the Riemann hypothesis suggests there's this astonishingly beautiful hidden pattern of zeros in the complex plane that perfectly dictates the distribution of prime numbers. It suggests this deeply ordered structure at the heart of all numbers. But after more than a century and a half, nobody has been able to definitively prove it's true.
These mathematical glitches are so profound that the Clay Mathematics Institute actually established the Millennium Prize problems. Right now, a cool $1 million bounty sits totally unclaimed for anyone who can prove Navier-Stokes smoothness, the Riemann hypothesis, or the quantum mass gap. We desperately rely on these equations every single day, yet $1 million is just waiting for anyone who can prove why they actually behave the way we simply assume they do.
Throughout this animated explainer, we've seen how the universe transitions from perfect elegance, like light finding the fastest possible path, right down to chaotic paradoxes, spooky entanglement, and fatal mathematical errors. Which really leaves us with one final, provocative question. Will we ever discover a true theory of everything that irons out these glitches? Or is physics fundamentally broken, and we're just staring at the absolute limit of what human mathematics can comprehend? Thanks so much for exploring the edge of reality with me.